Other questions?
My only question is about those Lorentz transformations that you have on the board, so I feel like it will be answered.
Okay. So we'll sort of pick up there are a couple things I wanted to do before setting you loose to finish up Friday's activity. All right, so we have a relationship between the two different reference frames. Again, all of this stems from the fact that the speed of light is constant regardless of the viewer. And so if I have some reference frame zipping by, you can think about this as Earth and a rocket zipping by, if you want. The rocket's going at some speed u, or a velocity u to the right. And so the prime frame would be the rocket's point of view, and the unprimed frame is the Earth's point of view. And then flip it around, the Earth's point of view, rocket's point of view. So if I had something going on in the rocket, and I guess on Friday or last Wednesday, I wrote up the formula, but it's a simple enough derivation. So from the rocket's point of view, or the prime frame's point of view, I have a ball that is being shot forward at some speed w. And in Galilean relativity, the speed of the ball, well, try this again, the velocity of the ball with respect to frame s is equal to the velocity of the ball with respect to frame s prime plus the velocity of s prime with respect to s. Classic vector addition relationship there. Again, as long as those two are the same, then we end up with the velocity of the ball with respect to s. But it's not as simple when dealing with actual special relativity. So let's think about the distance that things are actually traveling. So from s prime's point of view, that the speed of the ball is equal to the distance based upon prime's point of view divided by the time. Just basically speed is distance over time. Again, we're not worrying about acceleration. That's why it's special relativity, not general relativity, or one of the reasons. And if we bring in the Lorentz transformations over there, that's just equal to gamma times x minus ut over gamma t minus x u over c squared. Obviously, the gammas cancel. And what I'm going to do is I'm just going to multiply top and bottom here by 1 over t. Now, all of these are non-primed here. So this is all, so if we're thinking of rocket and Earth, this is from the Earth's point of view. All these are Earth point of view things. And so what I end up with here is x over t minus u. So again, multiplying this by 1 over t, multiplying this by 1 over t, I get 1 minus x over t u over c squared. And x over t, that's just the distance divided by time from Earth's point of view. That's how far the ball travels, divided by the time it takes to travel there. So that's just the speed of the ball relative to s. So that's v minus u over 1 minus v u over c squared. Let's plug into here and see how that compares to Galilean relativity. So this, the velocity of the ball with respect to s is v. The velocity of the ball with respect to s prime is just w.
X prime over 2 prime.
And the velocity of s prime with respect to s is u. So I have this relationship here. And if I solve for w, what does w equal?
V over u.
V minus u.
Minus. Which is just the numerator of what we had over here. And that's always going to be the case. If you get it in Galilean relativity, you've already got the numerator and the denominator, same sign, and those two letters are the same as those two letters. So it's, sorry,
Can I
guys.
just clarify the point of views? You started out with saying it was S prime point of view, but later on you said this is all Earth's point of view, and I thought Earth was S and not S prime.
That is correct. So basically, we're in the rocket ship and I throw a ball forward at some speed. So I can measure what it is from my point of view. I can figure out the distance, the time. But back there on Earth, they're also trying to figure out how fast is that going relative to us. And so that's what, so we start out with, this is the speed relative to the rocket.
Yeah.
And we eventually end up with that in terms of what the Earth sees.
I did it. He hit it like once. I did it. He caused no harm to me. He caused no harm to me. So I was trying to undo it.
So let's just do a quick example. The rocket, the velocity of the rocket with respect to Earth is 0.5 times the speed of light. The velocity of the ball with respect to the rocket is 0.3 times the speed of light. So in my scenario here, velocity of the rocket with respect to Earth is, I label as U. The velocity of the ball with respect to the rocket, I label as W. I want to find V. Now, the way I've set this up here, I solve for W in terms of V instead of V in terms of W. You go through a very similar process. V is equal to X over T. You plug in these Lorentz transformations because this tells me what X and T are equal to. And you end up with U plus W over 1 plus UW over C squared. So this becomes 0.5C plus 0.3C divided by 1 plus 0.5C times 0.3C over C squared, which is 0.8C divided by 1.15. That feels right. Which is something absolutely spectacular.
.696 meters. This is the velocity,
Yes.
meters per second. No, I tried.
What units did I have over there?
Meters per second.
Zach?
C?
C.
Ah, right,
Now, if you wanted meters per second, you would multiply, you'd actually plug in the value for C, but
right, okay, I got you.
yeah, relativistic speeds usually are done in terms of some variation of C.
Right.
Alright, now, I don't know whether I addressed your questions, Anna, on the Lorentz transformations. So, do you wanna,
I guess I've just been struggling to figure out how to apply these to a problem, and seeing this little graphical, like seeing how you drew it out here really helps.
okay.
I'm still a little bit lost.
I did the total in the barn example, right?
Yeah.
Yeah, okay. So, questions?
I just plugged in 1 plus, and then the 0.5 times 0.3, oh, C is squared. I think I have the problem fixed.
Yeah, the C's cancel out, which is conveniently we had everything in terms of C.
Still not getting the 0.5, but that's just a
0.3,
math.
so it's 1 plus 0.5 times 0.3, because the c's cancel. 0.5 times 0.3 is 0.15. Because that's half of 0.3 is 0.15, and then 1 plus that.
Okay, got it. I see, thank you.
Other questions? Alright, let's. Want to erase this. And then the derivation.
Just to clarify, the question we were answering was how fast is the ball moving from the Earth's point of view?
Yes. Alright, so, let's say that from the Earth's point of view, the velocity of the object, particle, whatever happens to be, from the Earth's point of view, is 0.7 times the speed of light. The velocity of the particle or ball or whatever happens to be from the rocket's point of view is 0.8 times the speed of light. How fast is the rocket going with respect to Earth? So my recommendation with a problem like this is first set it up like a Galilean relativity problem. I got three relationships right here, so how do I combine them in terms of some sort of sum or equal? Well, I've got r first and r second here, so I could just do a velocity of PE is velocity of PR plus velocity of RE. Again, what I'm looking for is that these two are the same. And then the first letter here is the first letter there, the last letter here is the last letter there. Chapter 2 of the textbook. And so now, since I'm solving for RE here, I'm solving for this. Well, let's solve for it. That means I subtract that from both sides, so I have VRE is equal to VPE minus VPR. Subtracted that from both sides. And now I've got my setup for solving this. So I know what my numerator is going to look like. This is equal to 0.7c minus 0.8c divided by what? What's my denominator?
1 minus 0.7 times 0.8 over c squared?
Close.
0.7c times 0.8c over c squared.
So I get negative 0.1c over 1 minus 0.56. Negative 0.1c divided by 0.44. Negative 0.2.
C, no question mark.
Thank you for removing it.
Yes. And we subtracted instead of adding because of the values given to us, because it was VP and VPR.
Yes.
Okay.
Yeah. So from the Earth's point of view, this object is coming towards Earth.
Okay.
That's what that negative right there means. questions? Because we're about to apply this.
This is not applying. That was a question.
That, we're about to apply it to a different situation. All right. Let's flash back to the thrilling days of yesteryear. I have a 3 kilogram box sliding along at 48 meters per second. It's going to hit a box that's 5 kilograms here, that's going at 0 meters per second. They're going to collide, stick together. So perfectly inelastic collision. So afterwards, basically it's an 8 kilogram box traveling at some speed v. How do you solve it?
P equals mv,
All right.
so we'll have 3 times 48 to get the momentum of the first box, which is something less than 150. 2, 4, 6, 6 less than 150.
144.
Thank you.
Plus,
And
I'll go ahead and
0.
throw that part in, 5 times 0.
Thank you.
And then afterwards,
You're on a roll, Anna. You got this.
8v.
all right. So I have 144 equals 8v. So what does v equal?
18.
444 eighths.
I was hoping for the whole number there. What is the unit? What are the units?
You got it. Units guy.
Yeah, it's got, that's all I'm known for.
It's on the board. Look at the top.
It's not safe.
Is it, okay, it's not C, all right, that rules that out. Is it, what, meters per second?
Woo.
You asking?
It is meters per second.
All right. It is
I'm
meters per
telling.
second. All right. Classic conservation of momentum. It's one of the problems that we started out with. All right. So now we're going to shift reference frames. Still classical mechanics, 151 stuff, 251 stuff as well. This time, instead of, we're going to call this the lab frame. In other words, you're standing in a lab and you see this object go by at 48, at 100 and something miles an hour. Going to smash into something else and we'll stick together. Now I want to go into the zero momentum frame. And in the zero momentum frame, I'm basically traveling however fast it's going after the collision. So in the zero momentum frame, I'm going to be traveling, this is lab, I'm going to be traveling at 18 meters per second. So that this object will not be traveling as fast, this is going to be coming at me, and this is standing still. I know in the zero momentum frame that the final, if they stick together, the final's not moving. So before, I have my 3 kilogram object going to the right at how fast?
So before, is that what you said?
Before, yes.
So 48 meters per second?
That's in the lab frame, but in the
Okay.
zero momentum frame,
Okay.
if you're cruising along at 18 meters per second relative to the lab, let me change the question. How fast is the 5 kilogram mass going in this new frame?
Okay, so zero momentum frame.
Yep.
And so what's going at 18 meters per second?
The observer.
The observer is going at 18 meters per
Yeah.
second.
It's like we set up the lab on the table here and said, so the lab frame is people who are standing still relative to the table in the
Okay.
experiment, or to the table. And now I'm going to observe it when I'm moving.
Right.
So it, okay.
So then the 5 kilogram mass at the beginning is going negative 18 meters per second.
All right, so 18 meters per second to the left.
Right.
So I guess I didn't define that, so.
Yeah, I get in trouble with double negatives. And then this would be 48 minus 18
Yep.
meters per second.
That's going at 30 meters per second. So my total momentum should be 0. We can just do a quick total check here. So that'd be 90 meters per second plus 5 times negative 18, which is negative 90. Oop. Watch those units there. That's really kilogram meters per second. Or Newton seconds. And we get 0.
And we change from meters per second to Newton seconds in this frame only? Oh,
We change, this is momentum here, so it's kilogram meters per second, which is also a Newton second. These aren't speeds, this is momentum.
okay, so down here, this 144 would have also been kilogram meters per second or Newton seconds?
Correct.
I see.
Correct. There we were trying to find the final speed here.
Yeah.
And it,
Yeah.
basically, momentum is still conserved in this new frame. So this, if you just subtract 18 from all the velocities, you get 30, negative 18, and this would be 0, which it all matches. Life is good. Momentum is conserved.
Yeah.
Questions on this, because we're about to make it relativistic. Make it relativist. So we'll do it all in terms of the speed of light. So conservation of momentum. There's a mistake in this, and deliberately so.